Thầy có thấy slide không ạ?
Ok, mình thấy slide rồi em nhé. Rồi, xem cả lớp trong đủ chưa? 29 bạn. Lớp có bao nhiêu người tham gia nhỉ? 5 mấy đúng không?
Vậy em xin phép bắt đầu.
9 người.
Good afternoon, everyone. I am Thanh Lam from Group 6. Our group includes 4 members. Me, Nguyễn Duy Hưng, Nguyễn Hoàng Nhật Quang, and Lê Hải Sơn. Today, we will together present our project of object detection. The main contents of our presentations are overview, dataset, data augmentation, YOLO v3 model, SSD model, training, some discussions, and future work. Let's start with the overview of our topic. So, object detection is one of the most fundamental tasks in computer vision. Its duty is to detect instances of visual objects of certain classes in digital images. The state-of-the-art object detection methods can be categorized into 2 main types, one-stage versus two-stage object detectors. In spite of achieving the highest detection accuracy with the region proposal step, two-stage methods can be computationally expensive and thus unsuitable for real-world, real-time applications. On the other hand, single-sort models incorporate all localization and detection duties in a single forward sweep of the network, resulting in significantly faster detection while requiring less hardware to deploy. In our project, we use 2 single-sort models, SSD300 and YOLO v3. Next, about the dataset, we use Pascal Visual Object Classes datasets from years 2007 and 2012. These datasets contain around 22,000 images with a total of 20 classes. Both train and var datasets are used for training phase, while the VOC 2007 testsets will serve as our test data. Next, data augmentation is the key for improving the network generalization abilities. In this project, we have used 2 common techniques. The first one is photometric augmentation, which means transforming the RGB channels of the original images, which mean random brightness, contrast, hue, light, noise, and saturation. And the second one is geometric augmentation, which it map each pixel of the original image onto a new position in a new image. We did random vertical and horizontal flip, random expand, and random crop. Next, so we'll present the details about our YOLO v3 models.
Okay, so let's begin by understanding the fundamental of the model. YOLO uses convolutional neural network for object detections. It can detect multiple objects on a single image, and YOLO algorithm is based on the idea that we divide the image into a grid with size S, and each grid cell is responsible for making predictions of the bounding boxes. And YOLO makes only the cell containing the object midpoint responsible for predicting the bounding box. This means that only one grid is responsible for each object bounding box in the image, and YOLO v3 extract feature from 3 different scales and predict using similar concept to feature pyramid networks. And basically, YOLO v3 model has 2 different parts: feature extraction and bounding box prediction. So first, go to the feature extraction part. In the feature extraction, YOLO v3 used .NET 53 model, which had 53 convolution layer with residual connections, and we ignore the last 3 layer of the .NET 53. So if the aim was to perform the classifications, then the layer could be added. But in our case, we are using .NET 53 only extract the image feature, so 3 layer will be not needed. And with the depth increasing, sometimes network accuracy gets saturated, which leads to higher training error. So this problem, residual block would introduce. and image input can be any size, but will be resized to some number that divisible by 32, such as 320 or 618 or 416. And we would like to detect classes along with the location. So we would be appending a detection head to the extractor, and the detection head is multi-scale. So we would need to extract features at multi-scale as well. So next, in the prediction part, the network use a convolution layer, upsample layer, skip connections, and a series of 3x3 and 1x1 convolution operations, which are used to improve the degree of nonlinearity, increase the generation performance, improve the network accuracies. And skip connections carry the input to a deeper layer. We don't do any kind of pooling layer to downsample the input image. At the pooling layer, lose more low-level features from the input image, and instead we use a convolution layer with strike 2 as a downsample layer. And this network, this network predict bounding boxes on downsample image for fast real-time predictions. And YOLOver 3 makes bounding boxes predictions at layer 82, 94, and 106, given by downsampling the dimensions of the input image by 22, 16, and 8 respectively. We can see that in the image, the network used 3 different branches from the DOCnet 53 model, and we add some convolution layer after the last layer of the DOCnet to get the first output, layer Y1, and the layer is 20 times smaller than the actual image. So next, we upsample the layer 2 times and concatenate with the second output layer of DOCnet 53, as you can see. And after adding some convolution layers, we get the output Y2, and by the similar step, we also get the output layer Y3. And as you can see, 3-level detections have YOLOver 3 detects different size objects more accurately, and so large objects get detected more frequently on layer Y1, medium-sized objects on layer Y2, and small objects on layer Y3. And this 3-layer detection technique have YOLOver 3 to get better detections than previous versions. So next, from our base feature extractor, we add several convolution layers. So the last of which apply a 1x1 kernel on downsample image to predict a 3D tensor, which encode the bounding box, coordinate, object list score, and class predictions. So for example, we downsample 416 by 416 image to 13 by 13 output, and the image, so you can see that has been divided into 3 by 3 blocks, and for every block we predict 3 bounding boxes. So actually we want to predict 3 objects whose center lie in the particular blocks. And let's get into more detail in the next slide. We get 4 bounding boxes of sets and 1 object list score and class probabilities for each boundary box. And sorry. So we will predict 25 value per bounding boxes and 75 value per cell total. And XY is a centroid offset. W and H is the value of width and height of the bounding box the cell predicts. And the object list score, this score is the confidence score of whether this block contains the center of any objects in the actual image. So that means if there is no objects, then the target is 0, and otherwise it is the intersections over union between the predicted box and the target bounding box. And class probabilities, and we have 1 probabilities per categories for each cell. Next, in practice, predict the width and height of the bounding box lead to the unstable gradients during training. So they introduce anchor boxes, which is an idea also seen in the previous object detection paper. And an anchor box is essentially a set of width and height chosen to represent the part of the training data. So for example, a standing rectangle may suit a human, while a white rectangle is better fit for a car. So using anchor box is a way of encoding knowledge about the training data into model to have the model to make appropriate bounding box predictions. So the model will predict how much the choose bounding box is offset in comparison with the anchor. And 3 anchors are assigned in every scale. And the anchor box anchor to grid cell and share the same centroid. So to determine these anchor, YOLOver3 apply a k-mean clustering and select 9 cluster. Next, so the output layer predict bounding box coordinate, dimensions, and object need score and class probabilities. So as the attributes are just the result of some convolution layer of the network, so the value of these attribute can be anything. So the value is transformed by some functions. So here are some function. Bx, by, bh, bw, bh is the centroid, center, width and height. I convert from some function I give here. Next, it's very common in YOLOver3 that multiple bounding boxes predict the same objects. So we need to keep the one with the highest confidence score and eliminate other bounding boxes with the high overlap rate and low score. So this technique is called non-maximum suppressions. And this method takes out the largest bounding box and remove the overlap bounding box, which has the IOU E larger than the threshold. So next, about the loss function. We regard the target detection task as a regression problem, and so the loss function of YOLOver3 divided into 4 parts. So this is the first equation. You see the total loss functions, and there are no object loss, objects loss, box regression loss, and classification loss. And we have the lambda is a constant to signify the importance of each part of the loss. And we apply binary cross entropy loss for the no object loss and object loss. For the box coordinate, we simply use the mean square error loss. And for the classification loss, we will only incur a loss for cross predictions where there is an object, and our implementation differ slightly from the paper that we use cross entropy, and in the paper they use binary cross entropy to predict several labels, like yeah. So next is about SNE, and Quang will present to you.
Okay, so about the SD single shot multi-box detector module. So at the time the paper is published in ECV 2016, SD is a state-of-the-art network for real-time object detection. So the 2 main characteristics of SD are discretizes the output space of bounding boxes into a set of default boxes over different aspect ratios and scales per feature map location. And at prediction time, the network generates scores for the presence of each object category in each default box and produce adjustment to the box to better match the object shape. Next slide. About the network architecture, SD is a composition of 3 parts. The first part is the base convolution derived from an existing image classification architecture that we provide lower level feature maps. And the second one is auxiliary convolutions added on top of the base network that we provide higher level feature maps. And the last one is prediction convolution, which locates and identify objects in these feature maps. So next slide. About the base convolutions, we employ the VG16 architecture pre-trained on the ImageNet as the base network. So as the authors of the paper, we have to make some changes to this pre-trained network. So the input image size will be 300 by 300 instead of 24 by 24. And the third pooling layer, which halves the dimensions, we use the mathematical ceiling function instead of the default floor function in determining the output size. And we also modify the feed pooling layer from a 2-2 kernel and 2 try to a 3-3 kernel and 1 try. And in the Convo 4.3, we add L2 normalization. The last one is that we remove FC8 away completely, and the FC6 and FC7 turn into convolutional layers through the use of Oichot's convolution, which is an alternative for the downsampling layer. So this allows the convoluter to look at the larger areas of input without a decrease in the spatial resolution, and also reduce the number of parameters to be learned, as we will have to stack some more convo blocks on top of the base network. So next slide. About the auxiliary convolutions, from the base network before, we stack 4 more convo blocks, each with 2 layers on top of the base network. So these convolutions provide additional feature maps, each progressively smaller than the last. And the size reduction happens through pooling in the base network, stride equal to every second layer. Next slide. So the last one is the prediction convolutions. So about the prediction convolutions, since each feature map item corresponds to different location and patches in the original image, the feature maps at the beginning of the network allows for detections of small objects, while those at the end of the network allows for detection of large objects. As you can see from the slide, the feature maps used to construct SD300 with BGD16 base network are Convo 4.3, Convo 7, Convo 8.2, 9.2, 10.2, and 11.2, which are covered by yellow frames. From the table on the left-hand side, you can see that the priors or default boxes are manually but carefully chosen based on the shapes and size of round-trip objects in our dataset. By placing these priors at every possible location in a feature map, we also account for variety in position. For example, Convo 10.2 has feature map dimension 3.3, so there are total 9 cells. Each cell has 4 priors or default boxes, so there are total 36 priors for these feature maps. So as you can see, there are a total of 87 and 32 priors defined for the SD300s. So basically, each image go through the module gonna have nearly 9,000 default boxes. Next slide. So from each feature map before, we will have 2 3x3 convo filters per feature map. So the first one is bounding box prediction, which predicts the offset of the bounding box. For example, the object is a little bit off to the right of the default box. So when it goes through the predictor, it's going to output the offset to trick the coordinate of the default box for better match of the object. And the class prediction is a probability score for the bounding box, 20 classes plus the background. Next slide. About the loss function, the SD loss function includes the localization loss is the average smooth L1 loss between the encoded offset of positive match localization boxes and their round truths. And the confidence loss is simply the sum of the cross entropy losses among the positive and hard negative matches. In this particular case, the authors have decided to use 3 times as many hard negatives as positive matches. So the total loss is the aggregate of the 2 losses combined in the ratio alpha. So for SSD, however, we simply use alpha equals 1 as the author's recommendation. Next slide. About the decoding outputs, as is quite similar to YOLO, so I'm not gonna into detail of this one. Basically, we have these steps: bounding box decoding, confidence thresholding for each class, and non-match suppression. Next slide. Sơn will present this slide.
So first I will talk about some concept here. So we use matrix precision to measure the abilities of the model to identify only relevant objects, and recall is used to measure the abilities of the model to find all relevant case or ground truth bounding boxes. So by setting the threshold for confidence score at a different level, we get different pairs of precision and recall, and with recall on the x-axis and precisions on the y-axis. We can draw the precision recall curve, which indicate the association between 2 metrics. And the important metrics we use here to compare among models that although the precision curve recall curve can be used to evaluate the performance of the detector. It's not easy to compare among different detector. So it could be better if we have a numerical matrix that can be used directly for the comparison. So this is where the average precision AP, which is based on the precision recall curve, come to play. And AP can then define by us the area under the interpolated precision recall curve, which can be calculated using the following formula. This is the formula. This is the mean average precisions, either mean of AP across or K classes, and we have 20 classes here. So next. So in the YOLOver 3, we try a training model from scratch and all using the pre-trained weight darknet 53 on which is trained on ImageNet, and changing backside. We change backside between 16 and 32, and also change the image size between 320 by 320 and 146 by 146. Sorry, 416 by 416. And MAP when change the backside don't change much. They both remain at around 40% of MAP. And as you can see, MAP show a huge difference among model using pre-trained weight and not using pre-trained weight. So a model using pre-trained takes around 200 epochs to stay stable at around 40% of MAP. On the other hand, the other takes only around 100 epochs to achieve approximately 70% of MAP. And next, 10 to our size image model only takes around 3 minutes per epoch, faster than the other, but only achieve 65% of MAP. Which is 5% less than 420 image size. And loss functions still have a tendency to decrease after epoch 100 or 200, but the MAP value among these models stabilize. So we stop training further. And next slide. Here the precision recall curve for class TV and the AP among 20 class among model. Yeah. The next one we'll talk about.
So in SD, we train with stochastic gradient descent in batches of 32 images with an initial learning rate of 1e-3, the momentum of 0.9, and 5e-4 weight decay as the paper recommendations. So due to time and resource constraint, we start with epoch 100. So from the graph, we can see the module accuracy can be higher with further training. This module achieves nearly 74 MAP. And the next slide. So here are the PR curve AP plots. Hopes, cat, and bicycle are top 3 highest accuracies. Meanwhile, bottle, chair, and botted plants are top 3 worst performance. So this is mainly because the top highest accuracy objects in the dataset are often large, distinguishable, and therefore can easy to detect. On the other hand, bottles, potted plants are small objects, and tray often go along with sitting pupil, which make it harder to be detected. So Hung gonna discuss more about it in the upcoming slides. So Hung, over to you.
During the inference, we have some comments about the model. First problem is labeling. As you can see from the slide, some images, YOLOv3 can detect objects with very high accuracy, which do not appear in the raw truth, like the chair in example 1, which is partly covered by the hand of the man, and the back of the car in the bottom right of example 2, and that is a part of the reason why YOLOv3 MAP is much less than SSD. And next slide. There also is some wrong detection, especially for small objects. One potential reason for this is that the earlier layers, which have smaller receptive fields and are responsible for small object detection, are too shallow to capture the information of the image. This problem can be fixed by increasing the input size. As we can see, performance increase from 320 to 416 of input size in YOLOv3 in the previous slide. We've also found that the small objects and adjacent objects are very hard to detect, which is a common disadvantage of ASD. This problem can improve by adding more bounding boxes and refining the scales and aspect ratios more accurately. In next slide, we will talk about the future work. As you can see, we stopped our training at epoch 100 due to time or resource constraints. We believe that future training can be improve the MVP of the model because the training loss was still decreasing nicely when we stopped the training. From the discussion section, we think that model accuracy can be improved by refining the labeling. For ASD, using stronger base network like ResNet, inception, exception to improve the performance, or MobileNet for better inference time. Using k-means clustering on custom dataset for to identify the right box sizes. Using higher resolution image to improve the performance on small objects, as well as the overall accuracy of the model. And finally, is the real-time object detection. That's all our presentation. Thank you for listening.
So thank you. Is there any question for the group? I think that you should turn on the mic and discuss person with the group.
I have a question.
Okay, so
how did you choose the coefficient in loss function of YOLOv3?
I set the, so can Lam turn the slide to the loss function of YOLOv3. So I set the lambda class E equal to 1, lambda of no objects E equal to 10, lambda to objects E equal to 1, no objects E 10, objects E1, and for lambda for box is 10. So that means I value the lambda box and lambda no objects more. However, I don't think that there any magic in those. It still work if you set all the number equal to 1. But I see that when I use the coefficients 110, 110, they coverage. They have better coverages. So I use that, but it didn't change much if they will change the coefficients.
Okay, thank you.
I have a question for you. Why localization loss in the SSD is L1 instead of L2, for example?
Okay, so for this question, because Smooth L1 loss is a robust version of L1 loss that is less sensitive to outliers than the L2 loss using, for example, RCNN and SPPNet. So when the regression targets are unbounded, training with L2 loss can require careful tuning of learning rates in order to prevent exploding gradients. So that's why here we use the Smooth L1 loss. So Smooth L1 loss is also, if you notice, is a special case of the Hilbert loss with the alpha equal to 1. So that's my answer.
Okay, thank you.
I have a question. How can you find Anthrobox, and can it be applied to other datasets? Do you hear me?
Yes, I can hear you. Lam or Hung, can you answer that question?
Yes, about this question, we use 9 anchor box based on the paper and normalize it with our image. These 9 anchor boxes are typically built for Pascal VOC. It can be applied to other datasets. However, the performance is certainly not as good as when you find your own anchor box, which is suitable for your custom dataset.
Thank you.
So I see the questions of Hoàng Văn Khánh. What is the improvement of YOLOver 3? So I only did a research on YOLOver 1, YOLOver 2, and YOLO 19 and 900, and I can see that with YOLOver 3, I have a new backbone, .NET 53, which is redesigned with the additions of regional blocks, and they also have multi-scale predictions, which optimize the feature map with different size, and they also have a skip layer concatenate that as the link between prediction layer is upsample predictions layer and concatenate with the previous layer. So this help increase the accuracy. There are also logistic regressions for confidence score, and YOLOver 3 use logistic classifier instead of a softmax to predict classes among.
For the question of Boom, according to the authors, ConV4.3 has a different future scale compared to the other layers. They use the L2 normalization technique to scale the future norm at each location in the future map to 20 and learn the scale during back propagation. With a learnable scale values which is very small. As you can see the detailed explanation of this problem in the ParsNet paper. I will send you the paper and you can.
Oh, okay, thank you. I will read your paper for more detail.
Okay, I will send you.
So we got new question from Lê Trường Giang.
You said if you have a custom dataset, then we need use K-mean for recompute the anchor. So how you method it? I think that when we read the paper, they said that they found the anchor boxes. For example, in the Pascal VOC, they just do experiment, do experiment, and that's the. Yeah, they know, they measure if the new anchors are better than the old one just by doing experiment. I just research. I just use the anchor box which we already have on the paper, and we not spend too much time on using K-means for recompute the anchor.
What you mean about the experiment? That they retrain the model?
Yeah, they train the model. I think that they train the model and have the result and just yeah, kiểu chắc là họ thử nghiệm thôi, bởi vì là Sơn, bởi vì đọc qua thì cũng không thấy có về cái vấn đề đấy, nhưng mà có vẻ là họ thử như vậy.
Mà tôi nghĩ nếu mà họ thử tôi nghĩ là nó tốn khá nhiều thời gian và
đấy là lý do và sử dụng Pascal VOC và nó có anchor box sẵn đấy, và không phải lo nghĩ về cái vấn đề tìm anchor nữa, bởi vì cái vấn đề tìm anchor thì cũng có vẻ là một cái vấn đề cũng khá là to và rộng. Đó.
Thì tôi nghĩ là họ sẽ có một cái là một cái threshold nào đó để có thể fit được cái anchor mới vào thế nhỉ?
Cái phần đấy thì tôi chưa, nhóm của tôi chưa tìm hiểu quá là nhiều cái đấy.
Ok, cảm ơn các bạn.
Okay.
So is there any question? Any more question for the group? Okay, so can you go back to the evaluation part of the discussion above the slide? Yes, the other slide, the previous one. The one that you measure the AP and the loss, yes. Okay, about this evaluation, is this something you done with the training set or for the test set? I see the loss, so it should be for the training set, right?
Yes.
So, can you confirm that this is for the training set?
Quang. Can you confirm?
This is for the training sets actually.
Is there any evaluation for the test set?
Yes. I not put it here. So it's about 742 MAP actually.
72?
Yes.
72. Okay, so did you do the comparison between the SSD model and then the YOLO version 3? Which one is better?
So in the discussion part, as you can see, Lam, can you move to the slide of the, here, as you can see, the SD on data on our project, the SD model is better performance than the YOLO V3, which is around 69 MAP. So as you can see, there are some problem about the round truth here. Aten explained previously. So for example, in the YOLO V3 module, it can detect, for example, in the middle, in the example one, it can detect the chair, which is covered by the hand of the man, and the chair is not on the ground truth. Actually, it's not on the ground truth, but the YOLO V3 still can detect it, so it's gonna lose its performance a little bit over the SD, which predicts quite well equivalent to the ground truth. And for example, the example 2, the SD, the YOLO V3 still can predict the back of the car, which does not appear in the ground truth at all, but still have very high accuracy. So there's some problem with the labeling that we still not solve this problem yet. So in our project, the SD is have a better performance than the YOLO V3, but it doesn't mean that YOLO V3 have actually bad performance, because it's not similar to the ground truth.
Okay, so for the work you use YOLO version 3 and SSD on the popular data sets. So what was the state of the art for this data set with the same model you are using? Is your performance better or similar or higher?
Okay.
Yeah.
In YOLO V3, I search on the internet, and there are 1 or 2 works that can reach the 80% of MAP, but the other often reach the MAP above 75, around 75 or less. So we reach 70%. I think that's quite fine.
Can you elaborate a little bit on the reason why you are not having the similar performance as the other? I mean, why the performance is slightly slower, smaller than the work of the other?
I think because we train not enough. We train stop at epoch 100. Why in the papers they train for like 32 epochs actually. And about the training slide, I said that we have the weight decay, but actually in in our training process, we haven't reached that phase yet. The wet decay is occurs in around epoch 154, and we just still hit the epoch 100. And so that's why in the discussion we have discussed that we can we can achieve the better performance if we training further.
Did you apply any type of pre-processing for the image, like the image augmentation or whatever like that?
Yeah, we apply.
I didn't see in the slide, right?
Yes, I did present about that, about data augmentation.
Okay. Which is the slide number? Number 5. Okay. Okay, so okay, I think that I have no more question for you.
To Phạm Quát Vũ and Nguyễn Việt Hoàng, we applied the non-max suppressions on the result. With the threshold of IOUs, we use 0.45, 0.45.
I also want to ask that did you implement the non-max suppression on each class or the whole class? For example, if let's see, two bounding box, one predict that there is a cat with 0.85 and one predict there is a dog with 0.09, then you would keep both of them, or you would just choose the dog with a 0.09 with a 0.9.
Quang ơi, Quang nói về của Quang trước đi.
Okay, so can you repeat the question?
Mình nói tiếng Việt nhé, thì tức là giả sử mà có hai cái box mà nó trùng nhau khá nhiều, thì một box đoán là có một con mèo với xác suất là 0.85 và cái box kia thì nó đoán là đấy là con chó với xác suất 0.9 ấy. Thì khi mà cậu áp dụng cái non-max suppression thì là cậu áp dụng với tất cả class, tức là chỉ chọn cái cao nhất thôi, hay là cậu sẽ chọn cao nhất cho từng class, tức là cậu sẽ giữ cả chó và mèo, hay là cậu chỉ chọn đấy là con chó thôi?
Giữ cả hai, tức là trong cái lúc đầu thì nó sẽ match với cả tức là cái ground truth nó sẽ match với cả một cái cao nhất, xong rồi nó sẽ suppression cho từng cái class đấy, chứ nó không ấy lẫn vào nhau.
Your level 3 cũng thế, nó cũng xếp từ cao đến thấp, xong rồi nó lấy cái cao trước rồi.
Ok, cảm ơn hai cậu.
So that's all. Thank you so much.
Ok, cho mình xin thông tin các bạn tham gia vào trao đổi nhỉ.
Nguyễn Việt Hoàng ạ.
Nguyễn Văn Thanh Tùng ạ.
Phan Mạnh Tuấn.
Nguyễn Vũ Thiên Trang ạ.
Em đợi chút mình ghi Nguyễn Việt Hoàng. Rồi, ai nữa nhỉ?
Nguyễn Văn Thanh Tùng ạ.
Phan Mạnh Tuấn ạ.
Nguyễn Vũ Thiên Trang ạ.
Mình đến Phan Mạnh Tuấn.
Nguyễn Vũ Thiên Trang ạ.
Thiên Trang.
Lê Trường Giang ạ.
Lê Trường Giang đúng không?
Vâng ạ.
Hoàng Văn Khánh ạ.
Phạm Cát Vũ ạ. Còn ai nữa không nhỉ? Phạm Cát Vũ rồi.
Còn các thành viên của nhóm em nữa.
Rồi, mình thấy nhóm em như tham gia khá đông đều đúng không?
Vâng. Em cảm ơn thầy ạ.
Rồi, chào em. Ok, chúng ta giải lao 5 phút nhé, sau đó chúng ta sẽ đến bài trình bày của nhóm tiếp theo. Nhóm tiếp theo lưu ý là chúng ta upload slide vào trong cửa sổ chat nhé, để cho các bạn có thể là tiện theo dõi.
Vâng.
Ok, chúng ta có thể bắt đầu với nhóm 9 được rồi đúng không? Nhóm 9 sẵn sàng chưa?
Dạ, bọn em sẵn sàng rồi ạ.
Ok, mời nhóm em trình bày.
So, dear professor and friends, the challenge for today is how to generate images with only dozens of data. As you may already know, with the recent development of deep generative models, it is becoming possible to generate high-quality images with both fidelity and diversity. However, the training of such generative models requires a large dataset. So, how to reduce the amount of data from hundreds of thousands to only hundreds, or even just dozens? The harder it gets, the more we want to solve it, right? We use a method for transferring prior knowledge of pre-trained generator, which was trained with a large dataset, to a small dataset in a different domain. Using such prior knowledge, the model can generate images leveraging some common sense that cannot be acquired from such a small one. We introduce to you our project, Transferring GAN Unlimited Data. To start with, I'll introduce you a very brief outline. We are going to go through 4 main parts in this presentation, which contains a problem statement, an introduction to our transferring method, batch statistic adaptation, then pass by our final model and finalize with the empirical experiments. So first, we introduce skill and shifts for filter selection. As you already know, a convolution can be seen as a combination of filters that convert a 3-dimensional tensor into a scalar. The number of filters is the same as the number of output channels. In this case, applying the scale and shift to the results of the convolution operation is equivalent to the following formula on the slide. Here, W is a 4-dimensional tensor representing the weights. Wi represents the ith filter, and Cout is the number of output channels for the convolution. This means that changing the scale gamma is equivalent to changing the activation strength, and changing the shift beta means modifying the activation threshold of the filter.
Inherit the idea of seed and skew above. We apply the seed and skew to the parameter for the Hurricane generator. Here, Z is the Hurricane generator, ZL is the output of L layer of generator, Z adapt L is the output of L layer after adaptation, and gamma is the skew parameter, beta is seed parameter. Because gamma and beta are used in the bulk normalization layer, we update seed parameter for the skew and seed without adding new statistic parameter. The figure here shows the bilayer model about Z here. Z is a latent vector. Each image will have a different Z. We will estimate the latent variable Z for all training data, such that the reconstruct data and reconstruct data are close to the training data. About the byline, let Zi go through the generator, output the reconstruct of image xi, and the learn parameter here are gamma, beta, and Z. The idea here is we learn Z for all image in dataset and regularize Z at standard normal distribution. When inferred, we sample Z and feed it to the generator to generate new image. On the right of the slide is the log function. Ch, W, and D are the channel height, width, and dimension of each filter. Lambda here is a coefficient used to determine the balance of each term. Now I will explain each part in the log function. The first term is L1 log between reconstruct image and training image. Here, xi is a I image. Zi is a latent vector corresponding to xi, and epsilon is a small random vector. The second term is the perceptual loss between reconstruct image and training image. The perceptual loss is used to compare high-level feature like content or style between image. Here, CL is the output of L layer of the trained classifier C. Layer here are the layer used for the perceptual loss. In this project, we use VGG16 and get the filter after X value activation layer. The figure here is the illustration. Let the generate image and training image go into the pre-trained classifier, and the log is sum of L2 log between two tensor output at layer L. The last two terms are for the regularization. The third term is used to regularize as standard normal distribution. Here R is sample from standard normal distribution, and K is the number sufficient larger than the amount of training data. The fourth term is for the prevent overfitting like in linear regression. To summarize the log, the first and second term are used to make the generate image close to the training image at the pixel and the semantic level. And the last two terms is used to regularize Z as standard normal distribution and prevent overfitting. Here is a conditional but normalization architecture that using big gamma. Gamma and beta are using but normalization layer, but in the conditional but norm, instead of use gamma and beta as parameter, it output from a network with class embedding as input. Now, Tung will present the architecture of big gamma generator.
Let's turn to the big GAN architectures. The big GAN is a type of generative adversarial network that was designed for scaling generation to high resolution, high fidelity image. Here is the key concept of the big GAN architectures. The skip Z connection, share embedding, conditional batch norm, and shell attention. Here is a big GAN generator. As you can see here, the latent vector Z is split into chunks that have equal size, and each chunk is concatenated to the share embedding class, and that's part to corresponding residual block as a conditioning vector. The main pipeline is that first, the latent vector Z is split and passed into the linear blocks. Then it is sequential passed into two consecutive residual blocks, the non-local or shell attention block, and finally is the residual block again. Then we get the image. Here is the shell attention module. The image features are passed into three different 1 multiplied by 1 convolutional layers. Then two of them are combined into an attention map by applying matrix multiplication and shortmark operation. The attention map now is a matrix which in range 0 and 1 and indicates the extent to which the model attempts to synthesize information. Then it is multiplied with the third image features, and the region was passed into 1 multiplied by 1 convolutional layer to get the shell attention feature map. We have the same shape with the original feature map before passing into the attention block. So the shell attention mechanism allows the generator model to focus on different parts of the image. Here is the residual block of the big GAN generator. As you can see on the right of the pictures is the concatenated vector of the latent vector Z and the class embedding. The vector is linear projected to produce on the gain and bias for the batch norm layer as a conditioning vector. The main pipeline of residual block use a pattern twice the batch norm value and 3 multiplied by 3 convolutional layer interspread with an assemble layer in the first pattern. In residual collection, they use an assemble layer followed by one multiplied by one conversion layer to the feature map before adding them to the main residual pipeline.
So here is our chamfering BigGAN model. Firstly, the index passed through the embedding matrix return a Z with its 120 dimension vector. Doing the same for the Y, the label and getting a 128 dimension vector. After that, the Z vector is divided into 6 parts in the split, and the first one go down and the last 5 ones concave with the Y vector in the label embedding outputs and result in a 148 dimension vector. It then go into the skip connection. Look at the right. Inside the residual block, the concat vector is passed through 2 linear layers, each of which output shift and scale value. Then 2 values go into bus normalization layer. Our final model contains one embedding layer for latent variable Z from index of the image from dataset. Label of the corresponding image will pass through class embedding layer. We also add skip and scale parameter after the first linear layer. Luckily, gamma and beta are used in the conditional bus normalization, so we update this parameter for the scale and shift without adding new statistic parameter. For class conditional bus normalizations, the output of the linear layer here is shift and scale. So different gamma and beta value in the bus normalizations are used for each class label. To summary, the trainable parameter in our project are Z embedding layer, class embedding layer, first linear layer of the generator, new shift and scale parameter after the first linear layer, and linear layer with output shift and scale in the residual block. Our other parameters are frozen. We simultaneously estimate the latent variable Z for all the training data. The input is the index and the label. The output is the reconstruct image. We want to output image are close to the corresponding image in the training dataset in the training phase. When finished the training, we don't use the Z embedding anymore. Instead, we sample Z from the normal distribution to generate new image. And next, Trang will present about the trick we apply to the embedding space.
So now, after having a complete model, we want to add a trick to it. As we already explained to you, both the embedding matrices, including the class embedding, will be trained from scratch. However, we don't want to do like that. The inspiration for the modification came from the knowledge that some previous works observed via T-SNE visualizations show that the class embeddings learned by BigGAN capture well the semantics of the ImageNet classes. It means that when they projected 1,000 class embeddings onto a 2D T-SNE space, interestingly, the embeddings were reasonably located in the neighborhood of related concepts. For example, as you can see in the slide, most docks are located nearby. The semantically meaningful T-SNE arrangements of the BigGAN class embeddings motivated us to search in the neighborhood of an original embedding to find a new vector that yields a better image, which results in better embedding compared to normal initialization and train from scratch one. In detail, instead of letting the class label go straight by the embedding and then go into the generator, we pass it through a classifier first. By classifying all images of each label, the classifier will find top K classes in the domain of ImageNet corresponding to the original. For instance, the top 3 for label cat when mapping into ImageNet are the tabby cat, Egyptian cat, and tiger cat. Then we take the mean of the trained embeddings on these KE classes to be the initialization of our labels. So, did our initialization technique work? And how is the performance of our model? Let's find out the answer in the final parts experiments.
Hi guys, in the previous part, we already presented about our model and trick. In the next part, we will go into another part, it is dataset in evaluation. For the dataset here, we have animal faces that are images of dogs, cats, and wives. The image size is 128 square, and the dataset size are 45, 360, 1,200 respectively. Next, let's take a look at the picture. Why evaluating GAN model is hard? In the lab, we have a supervised image classification model. Then evaluation is straightforward. We just have to compare the predicted output to the actual output. However, in the right, with a GAN model, you just pass in some random noise to get an image and want this image to look as real as possible. So how exactly you can quantify the realism of this image? We have two metrics here to evaluating our GAN model. They are inception score and Friedrichs inception distance. First, inception score. This score was developed to an attempt to remove the subjective human evaluation of images. The score will capture two properties of a collection of the images. They are first, image quality. Do images look like a specific object? And second, image diversity is a wide range of objects generated. The image quality will be proportional to the inception score. Then the better image will have higher inception score. Second, we have the Friedrich inception distance. This metric indicates the distance between the features of original images and the generated images, and summarize how similar two groups are in terms of statistics. Because of the metric is distant, then lower score will indicate that two groups of images are more similar. When the inception score increase and the FID decrease, we will have the better model checkpoint. From that, we can pick a model checkpoint that generates a low FID and high IS for inference. Finally, we evaluated the given metrics, IS and FID for different settings. For the first setting, no conditional label of image and no initialization trick, we get a significant low inception score compared to the other setting. For the second setting, we tested on a model with no initialization trick. We saw a slightly increase on the FID score compared to the first setting. And the third setting is our original model. The metrics evaluated on this setting indicate the best quality images which have a high git inception score and low width Friedrich inception distance.
These figures show the images generated from latent vector Z sampled randomly from a truncated normal distribution, We use 0.1, 0.2, and 0.4 for the truncation threshold on dataset size 1200. We confirm that sampling with small truncation threshold can generate images with higher fidelity, and with larger threshold can generate images with diversity. Next, with the data size of 45, the reconstructed images show good quality. However, in this case, the data size is too small, leading to difficulties when sampling random. As the size of the datasets increase, the reconstruct goes worse, but the random sample ones goes better. We can see that with only a very small dataset, the model converges stably without collapsing and can generate consistent images. This is because the method effectively reduced the pre-trained convolutional kernel parameters. Interestingly, the class embedding captures the overall shape of the animal, and the latent vector Z captures some characteristics like fur color, ear shape, and background color. Here is an interpolation video. Each row has the same latent variable Z, and each column has the same label, class label. Tung, can you share the screen? As the video shows, although the amount of training data is small, a smooth and consistent interpolation is achieved. And that's the end of our presentation. Hope that we brought to you an interesting experiment when working with limited data, as well as the transferring generative models. Thank you for your attention, and we would love to receive feedbacks and questions from you guys.
Okay, so thank you, group. Any question for the group 10?
I have a question.
9.
Okay, let's go on.
Why you don't use a discriminator in your approach?
I can answer this question. The discriminator used for distinguish between the real image in the dataset and the generated image. And the generator generates realistic image by using adversarial chaining. So adversarial chaining is effective when we have many data points and the data densely fill the distribution. But if we have small data sets, adversarial chaining suffer from overfitting, and the chaining process will be unstable and easy to corrupt. So we don't use adversarial chaining. Instead, we use supply chaining. Actually, this architect can be extended to adversarial when the dataset become bigger, and maybe it's better if we add a discriminator in the future. We will try to implement this. I think so. If we have more hardware and so on. This interesting idea.
Okay, about the question from Đặng Vũ Hoàng here. I can answer this question. When we increase the truncation threshold, then the space of the generate image will be stronger, will be smaller, and it will Okay. Maybe Chang will answer this question.
About third and Đặng Vũ Hoàng, your question, the truncated distribution for Z, it means that when sampling Z, the values which fall outside a range are resampled to fall inside that range. It's like a trade-off between image fidelity and image variety.
So can you explain to me what is the interpolation?
The interpolation is just a simple linear algebra in the latent space Z and the class label learned by the generative model.
Any other question? Okay, so can you go back to the slide? Okay, so I must say that you guys choose a very interesting topic, and it's quite, new topic to in comparison to other topic presented by your classmates. So I really appreciate that you choose this topic to work on. But honestly, when listening to your presentation and also looking at the slide, I think that you I don't know, but you have very interesting slide with animation and nice images, but somehow I really feel hard to understand the slide if I need to read the slide alone. Even though I listen to the presentation and look at the slide, I somehow really find hard to catch up with your idea. So can you go to the next slide? This slide is somehow the newer version than the slide I got in your submission. Is that correct?
Yes, it's correct. We have changed it.
Okay, so let's work on the newer version you have. So let's move to the second slide. Okay, so next one. Okay, this is at the outline of the talk. The next slide, please. Okay, so you start the discussion with discussing about the shape and scale for filter selection. I think it's not a good approach to start with this type, information. You forgot to mention about the problem, the context, the data sets, and why did you choose to start with shape and scale for filter selection? You assume that everybody understand about the context of the talk is something else?
I can reply to the question. Is the introduction to the problem is said by Chang before, but it's not in the slide. So, but I think the most important of our project is about shape and scale parameter. So we present this first.
Okay, so can we discuss a little bit about the data set and the objective of the problem?
Yes.
Can you show me a slide about the data set you have?
Wait me a minute, I will check.
Slide 19. 18, 19.
Do you see my slide?
Yes, I see the slide. Okay, so you have the data set AFHQ something, animate
Yes.
space high quality. Okay, so in this data set, you have the image size 128 by 128, and you have, how big is the data set size?
The data size about 30,000, 30,000, but the problem we want to solve is the limit size data set, so we try to use the subset of this data set in this project.
Okay, so you mean that you have three data sets, right? Small data set consider 45 images.
Yes.
So this is a total image for 3 classes, or is the number of image for each class?
Each class contain 15, so it is a total is 45.
Okay, so okay, the second, the medium data set is the 360 for 3 classes, right?
Yes.
And the bigger one you have is 1002. Okay, so the problem is to use a GAN model to generate the image belong to the 3 classes. Is that correct?
Yes.
Okay. So can you go to the architecture of the network?
Yes, here is our network.
So here is your network, right? So what is the input and what is the output of the network?
The inputs is we have 2 inputs. The first is the index of the image in the data sets. We label them from, for example, if we have 45 image, it will label from 0 to 44. And
okay.
The label we have 3 labels, so we encode it as 0, 1, and 2. And it will go to the embedding layer to output the corresponding vector.
So the embedding here is actually the embedding of the image, or that's the one hot encoding of the index?
We have 2 embedding, one for the Z vector and one for the label embedding vector.
I'm not talking about the label embedding, but I'm talking about the index, the embedding for
Yes.
the index.
It's not the one hot, it's the number.
Is the number?
And go through embedding, and is a learnable parameter. We will go to the embedding, and we have a 120 dimension vector. And it will learn, and in the load function we have
okay, so the embedding has nothing to do with the content of the image, is that correct?
That is correct.
There's nothing. Okay, and then the output is the image?
Yes, and in this problem we try to find the depth corresponding to the image in the training data in the training phase.
So you got the image as the output, and then you compare the image with the graph chart image.
Yes.
And you use the loss. Can you go back to the loss a little bit?
Wait a minute. Yeah, here our loss.
Okay, so here is the loss.
The first 2 terms is to calculate the distance from the reconstruct image and the original image in the training data. And the third term is for we want the Z embedding is follow the normal distribution. So when we sample the image after training, we can use the normal distribution to sample and generate a new image.
Okay, so can you go back to the architecture again? What is the image on the left and the image on the right?
The image on the left is the overall architecture, and the image on the right is the zoom out of the residual block.
Okay, right. But you have no annotation for the image, so no caption for the image, so it's quite hard for me to understand what is this. What is this?
Sorry.
Okay, so that's what the race. Can you go to the previous slide?
Previous slide.
So again, what is it? This is again the residual block.
Yes.
Previous slide.
What do you mean this slide?
No. The next slide.
Here.
No, previous one. I think that I can move the slide.
That's.
Okay.
You can.
Okay, so this slide is for what block? The non-local block?
Yes, it is the slide you want to talk.
I mean, you have the non-local block here, and you have the big image on the left. So is that the zoom out version of the zoom in version of the non-local?
Yes, this is a zoom in version.
Okay, it's hard for me to understand your convention. So the Z here is the index. Is that
Yes, you mean no? That is the output of the embedding layer. Embedding vector. That is the output vector from the embedding.
Output
from the training. But when we sample that from the normal truncated distribution. The embedding that here work only in the training phase.
So the embedding is a typical neural network, fully connected network, or what?
This is the lookup table.
The lookup table.
And we change and update this.
So what is the color code you are using on the image? Sometimes it's gray, sometimes it's violet. So what is the code for the color?
John respond for the slide. So
okay, about the overall architecture, I used purple for the rest block, and for the zoom in of rest block, I use purple for like a familiar block, and the special one I use gray. Is that okay?
I think it's fine. So you see at this point, you see the line layer, you coat it with the purple color, and then at some point in the last block, you see the line layer become.
But the okay.
So can you discuss a little bit more about the cell tension feature map? So this is output, right?
Here, you mean this line?
Yes, this line.
As Tung will present this part, but we do not update any parameter in this block. Just talk about began. So Tung will present this part.
This was the original architecture of the non-local block in the began, and we do not update the parameter in this layer.
Can you say it again?
This was the zoom out of the non-local block in the original paper of the cell tension GAN, and we do not update any parameter in this layer.
You do not update, but I just questioning if you understand the way this non-local block work.
Can you ask again?
I'm asking if you understand. Can you explain the way that this block working in the network?
Yes.
How the cell tension feature map works? Right?
You can see on the FX and GX. First, let me. First, the feature map is passed into first one multiply one convolutional layer, and you can see the FX and GX, and then two of them are combined into an attention map by applying magic multiplication and softmap. And the attention map now is a magic which in range 0 and 1, and this attention map indicates the extent to which the model attempts to synthesize the information. And the attention map was multiplied with the SH again, and followed by one multiply one convolutional layer to reshape the feature map into the with the same original shape. The key concept here is the attention map, which allows the generator model to focus on different parts of the image.
Okay, so the cell tension map here will be used to combine with where is it? Okay, this is the address block. Okay, so it's like, I mean, the layer before the last layer. Is that correct?
Yes.
So why not the last one, but the layer before the last one? Can you understand why?
Well, actually, can you go to the previous slide?
Previous slide. Yes.
Well, actually, it is the original architecture of the generator of the began. So we do not modify any the pipeline of the architecture. So after the non-local, there is a rest block, and we do not modify the pipeline.
Yes, but do you understand why we need the finder rest block? Why do we need that finder rest block?
Well, actually, I not really understand why we need rest block in the final. I think the non-local blocks is just cell attention to synthesize the information in different parts of the image, and we also need a rest block to how to say, I think the rest, I think they shouldn't use the non-local block to directly synthesize a complex image. So we need a rest block in the last layer.
It's not convincing enough for me to have more argument.
Well, that's all I can understand.
Okay, so any other question from the class?
Với câu hỏi của bạn Châu thì có thể đúng lúc mà mình sử dụng nhiều dữ liệu. Tức là nếu mà mình có nhiều dữ liệu rồi thì mình có thể sử dụng cái adversarial training. Nhưng mà với ít dữ liệu ấy thì tức là dữ liệu đã thưa rồi. Thì lúc sample cái Z thì mình sẽ ít có khả năng bị trùng hơn. Và nó còn phụ thuộc vào cái truncation normal của mình ạ.
Any other discussion? Okay, so I think that we reached to the end of the demonstration for the milestone projects. I think that we can have some moderation before you enter in the final examination. For the final examination, it will be open. It's open question examination. That means that you will you will have two parts. Let's say that I'm not sure, but maybe we will have the same format as the examination of the previous semester. We will have two parts for the final examination. A part will be 45 minutes. Let's say 45 minutes, and you will have the time to answer, write or answer for one question. So not one question, but one exercise. You have two exercise. Exercise will last for 45 minutes, and in each exercise you will work on some realistic deep learning problem. In the previous semester, we have one exercise about the natural language processing, and the other exercise is about the computer vision. So maybe we will have the same format for this semester, except that the time for each exercise is a bit longer. Now I think that we can have the exercise for 45 minutes. In the past, it's only 30 minutes, and some students complain to me that it would be too short for them to have the best answer for the exercise. So I decided that we will have 45 minutes for each exercise. You will have two exercise, and maybe, I mean, most probably we will have one exercise for the deep learning for natural language processing and one other exercise for the computer vision. You will work on realistic problem and you will give the answer for, I mean, the whole training pipeline for the exercise. And so you have to explain about the data preparation, neural network configuration, training parameter, hyperparameter tuning, and discussing about the result, the loss function and whatever, right? So the whole idea of the exercise to assess you guys, assess your understanding, your knowledge on deep learning after the classes. So is that clear for you about the final examination? And any question for the for clarifying the final examination?
Thế buổi thi sẽ diễn ra theo lịch của trường hả thầy?
Đúng rồi, diễn ra lịch của trường, nhưng mà chúng ta sẽ thi theo hình thức đề thi mở.
Dạ.
Thi trên mọi người sẽ thi hình thức online ấy, và mỗi người sẽ bật team lên, bật camera lên. Rồi chúng ta sẽ chia bài thi làm 2 phần. Làm hết một phần thì sẽ nộp bài và sau đó sẽ làm tiếp theo.
Có được dùng thời gian phần thứ hai để làm phần thứ nhất không thầy?
Không, tức là hết phần thi nào thì sẽ thu bài của phần thi đấy.
Dạ, vâng.
The pipeline cái pipeline đấy thì mọi người sẽ phải tự design, hoặc là trong đề thi cũng có thể có gợi ý, nhưng mà cơ bản thì mọi người sẽ tự design pipeline đó. Some sample question. I can give you the question of the final examination in the last semester, but I'm sure that this semester it would be different, a little bit different. It would not be the same. So, okay, wait me a couple minutes. Ok, thì đây là một bài ví dụ trong đề thi cuối kỳ của năm trước thì mình có thể xem qua. Mọi người có câu hỏi gì đâu nhỉ? Tiêu chí đánh giá. Tiêu chí đánh giá là các câu hỏi phụ đấy, bọn em có lý lẽ thuyết phục để bảo vệ cái quan điểm của mình. Mình cũng sẽ không thể đánh giá được là tại vì nó không phải là cái mã nguồn chương trình chạy được ấy. Thế nên là cơ bản thì là nó có là cái yếu tố gọi là cái tính thuyết phục trong các cái lựa chọn của bọn em thôi. Em phải đưa ra quan điểm và bảo vệ quan điểm đấy. Có ai câu hỏi gì nữa không nhỉ? Thực tế thì thi không sử dụng tài liệu. Thế nhưng mà trong những cảnh mà chúng ta thi online như vậy thì cái việc bọn em dùng tài liệu, mình nghĩ là dưới góc độ của mình thì tức là nó rất khó để kiểm soát. Thế nhưng mà mình hy vọng là chúng ta thi cử một cách gọi là văn minh và đúng so với commit, với cam kết. Có câu hỏi gì không nhỉ? Ok, chúng ta kết thúc môn học tại đây. Hẹn gặp lại mọi người trong buổi thi cuối kỳ và chúc mọi người thi thật tốt. Chúc cho mọi người là sau một kỳ học và kỳ thi thì mọi người đạt kết quả cao, rồi có thể áp dụng những kiến thức đã học, đã tìm hiểu trong công việc của mọi người trong những năm sắp tới. Chào lớp nha.
Vâng, em chào thầy.
Chào em.
Thôi thầy.
Với thằng hay với một phần.
Gần chưa bác?
Dạ với cả là
Hả?
cái là
Được nha, không phải nhé. Để cả làm một chuyện cái đường nguyên mà sau có thấy nó gặp nhé.
rồi được.
Hãy subscribe cho kênh Ghiền Mì Gõ để không bỏ lỡ